I guess we'll get started. We're at time, so everyone else that'll trickle in will come in. So I'm Carl Berg. I'm a principal engineer with Amazon Web Services. Within Amazon, I'm part of the Game Engine and Developer Services team. How you pronounce that as an acronym, we're still trying to figure that one out. It's kind of awkward, so we'll get there. I've been with Amazon for a little over 7 years now. And since starting there, I've primarily worked on, I guess the best way to put it is advanced technologies for scaling multiplayer and network simulations, which sounds fancy. It's basically taking like the AAA esport local prediction algorithms we use in games, like first-person shooters and such, and making that scale to simulations that are much larger than we're used to normally. So today, I want to talk to you guys about how you can author content using the multiplayer functionality we put inside Open3D Engine, such that it's going to work well within a large world environment. There's a number of problems there that need to be overcome. So to start with, I'm just going to go into like a basic introduction of like how multiplayer works in the engine. And that's just going to sort of give us a common set of definitions that we can sort of refer to as we go through the rest of the talk. Then I'm going to start talking about network entity roles. And this is really important because, you know, as soon as you start scaling from, even from just like a single client to like a client and a server, or, you know, 2 clients and a server, or, you know, many clients and many servers, like that simulation state, the game, is shared across all of those machines. And now you start running into issues of like write integrity, data integrity. We need to maintain like some sort of coherency there. And network entity roles are like a really critical piece that allow us to solve that. Once we're through the network entity roles, I'm going to talk about host migration, which is the first part of like really scaling this stuff up. I'm going to go into like why it's necessary, as well as like what are some of the implications there. Then I want to talk about the 2 communication mechanisms that we provide within the engine, specifically network properties and remote procedures. And I'm going to go into like a couple issues that you would normally have authoring gameplay code if you're more familiar with like writing single player code, and how you can use these tools to basically overcome those issues. Finally, I'm going to follow up with some interfaces that are in the engine, because if you've pulled down the engine and played with it, you know that we don't actually ship any large world tech with the open source engine, but the engine's very much capable of it. So if you're interested, you'll need to look at these interfaces in order to start implementing a lot of that. And then I'll do questions, but that'll have to be off camera. So to start off, as most of you are probably familiar with, Open3D Engine uses an entity component architecture. And that means like we have entities within the engine, and those entities contain a collection of components. Now, specifically for multiplayer, those components are multiplayer components. We have a specialized mechanism for defining those components, which is way outside the scope of this talk, but Gene had a wonderful presentation just yesterday that went into a great deal of detail about this. So if you want to know more about that and you haven't actually seen Gene's talk, I definitely recommend you go back and watch that once it's posted online. There's also a lot of like wonderful documentation online about how to author these multiplayer components as well. Now these multiplayer components, they have remote procedure calls, like 0 or more remote procedure calls and network properties. And each component is typically responsible for some like nugget or like piece of functionality within the engine, right? So like actual examples, we have the network transform component in the engine. And the only responsibility for that is to replicate your entity's position, your transform, over the network to all the other hosts in the simulation, which is really important when you want everyone to see everything in the same place, right? So additionally, for multiplayer, we add this concept of a controller. And these tie into the network entity roles that I'm going to be talking about. So they're really, like when you start talking about scaling up and having data integrity in a distributed simulation, there's really 2 major approaches you can take. One is to sort of allow anyone to write at any time to anything, and then detect the conflicts at some point later. So after the fact, you detect that there's a write conflict, and then you have to have some fairly complex logic that will merge that together and give you your new state moving forward. The other is to like have some sort of mechanism for exclusive write access, so that only one agent can write to a piece of data at a time. And rather than expecting our customers to write potentially intractable merging logic, Like you can just imagine like an inventory system. Trying to merge that together across a distributed simulation would be really complex. We've opted for the mutex approach, basically. So that controller essentially represents a write mutex. Now, being an engineer, I'm not particularly artistically gifted, so like any engineer nowadays, I did start off by like going to Stable Diffusion and tried to get it to like generate all my example art for me. And well, it did a far better job than I could ever do. It wasn't like iconographically simple enough for me to get the concepts across, so you're stuck with my MS Paint art. So this is a world inside Open3D Engine. And because this is a game, like some of these entities within the world are going to be player entities. And it's good to note that like within this world, like a lot of this will be loaded at load time when you first load the world, but also a large number of these entities are going to be spawned dynamically at runtime based on gameplay and simulation requirements. So some of those entities are going to be controlled by players. That means there's an actual client connected somewhere in the world to the server, and it's driving the behavior of this entity. Other entities are going to be controlled by the server entirely. They're server-controlled entities. So NPCs, AIs, like if you have a very physics-heavy simulation, rigid bodies that are entirely server-controlled using the physics engine. And we'll have some subset of entities as well that are basically just static. There's no interesting behavior of note on them. They're really just there to sort of fill out the world, provide proper optimal sight lines for a lot of these maps. But they don't really simulate, they don't really do too much. And actually this has a big implication on how stuff loads, but I won't go into the details about that. It's just good to know that those classes of entities kind of exist. So I'm going to talk about the network entity roles. So the first role I'm going to talk about is the client role, which does not have a controller. So we sort of break these roles up into both the client side and the server side. The first role, client, it basically is a read-only role on the client side, right? And you know it's read-only by the fact that it has no controller. The presence of a controller basically denotes write access. If you're familiar with Unreal Engine at all, then Unreal calls this their proxy. It's the proxy role inside Unreal Engine. So I'm going to take that same MS Paint world and I'm going to slap it onto the screen of a client. And Open3D Engine is primarily a server authoritative client-server architecture, right? So for this world on a client, you would expect the vast majority of entities inside the world to be in the client role. And I'm going to highlight those guys in blue here. So all of these entities are basically just read-only, right? So the server is responsible for updating all of their state. The server will replicate that state to us on the client. And our job as the client is basically to present those entities in a very visually pleasing way so that it looks smooth and we have a compelling gameplay experience for our customers. But that's really about it. So the next role is the autonomous role. And this is also still on the client side. But this one does have a controller. And by having a controller, it denotes that we do have some form of write access. Again, there's a server authoritative simulation. So this is a limited form of write access. So again, on the same client machine, we've got that same world. And one of those entities inside the world is going to be the player that we control, right? That's our guy that we're moving around the world and interacting with. It's our avatar. That would be the entity that would be in the autonomous role. So let me go back. By being an autonomous role, it does give us write access, but it's a limited form. We call it like predictive write access, essentially. So when you define your network properties, as you saw in Gene's talk, there's an attribute in there, like is predictive true? That basically allows you to write to that network property on your client. And the server and the client will both write to it, executing the same logic. There's sort of like a locally deterministic loop for the player. And they'll actually compare. They'll compare their state together. And if there is a desync, like if you do something wrong on the client, the server can actually detect that and it will correct you. So in the end, like if there is a mismatch between what the client and the server locally predict, the server will win. But it allows you essentially to process inputs. So like keyboard, mouse presses, controllers. You can see the results of those actions almost immediately on your client screen. There's no round trip delay here. And that sort of escalates the client experience to a level that our players expect. Our goal here is to make the server invisible. So the next role is going to be on the server now, and it has a controller. It's the authority. And this is the one everyone expects. This is the server authoritative, like full write access server role. So if I take that same MS Paint world and stick it on a server screen, if a server had a screen, which they don't, because it's a server authoritative network simulation, we would expect every single entity inside that world to be in this authoritative role. And this is where sort of like a typical first-person shooter engine sort of ends. However, if you actually look at the open source code base, the Open3D engine code base, we have a fourth role. There's 4 roles, not 3. And the fourth role is on the server side, but it doesn't have a controller, which seems kind of weird. The only way to make sense of this is for me to start looking at what happens if we have 2 servers, right? So imagine we had 2 servers here. We'd want the 2 servers to somehow split up the process of simulating this world. So I'm going to denote the entities that each server has control over, authority over, in orange. But we have all these other entities that are inside the world simulation. And some of these entities are potentially interactive, like they're within interaction distance for entities that the server controls, right? That means each server needs to have awareness of spatially relevant entities around it. And that's where our server role comes in, right? That basically allows servers to basically talk to each other and say, hey, here's a read-only copy of stuff that I own that you probably need to interact with. And that allows the 2 servers to properly reconcile their simulations. So to understand why we'd go through this trouble, because it adds quite a bit of complexity to the network layer, I'm going to go with a basic example here. So this is basically 250 simulated players. They're running all their basically random inputs, like they're going to move around, shoot, jump. You can't actually see the shooting because we don't have effects, but they're shooting. And this is all running on a single server. Let's see if the video plays. I hope it does. Nope. Technical difficulties, sorry about that. Okay, maybe I'll just pop out of the presentation and that'll work. Okay, so this is running on a single server, 250 simulated players. And as you can see, like we're doing all the local prediction, we're doing all the rollback. For server authoritative networking like this, like the rollback is pretty intense. That's a very expensive operation. And with 250 players, we just can't keep up, not on a single server. Now this is going to be the exact same simulation, but I'm running it across 4 servers. In fact, there's so many players here that you can't actually see them all on screen. We run out of memory. There's more players than you can see, but there are actually 250 players here. And now this is 4 servers that are interacting in real time together to basically distribute the load of all these clients, all these players, and keep the experience good. And with 4 servers, actually, it keeps up pretty well. We can actually maintain a pretty good simulation rate. So this comes down to the fact that simulation can be quite expensive, right? We've got stuff like pathfinding, we have AI subsystems, we have all the local prediction for our players, our clients, all the rollback operations to actually deal with lag compensation so that their interactions work as they expect. We have all the rigid body physics simulation, vehicles, like all that stuff. It costs a lot of CPU. And so to solve that, we basically need to look at ways of optimizing, right? So you can optimize stuff to a certain line. You can put a lot of work in and like fix up your physics, make the physics really fast, fix up your AI, fix up your local prediction logic, but at some point you're going to hit a red line. And at that point, like you've got diminishing returns. Your gains are going to be so small for the effort you put in that it's just not going to be worth it to optimize anymore. So if you want to scale beyond that, you need to distribute your simulation. And that implies some aspect of host migration, which we'll get into soon. Like if you want, well, there's a couple reasons: fault tolerance and elastic scalability, which are the two key terms here. We're going to require host migration for those entities. And as soon as you add that level of complexity to your networking layer, we want to keep that invisible to the clients, right? So our abstractions need to make that as transparent, like just not a problem for them to deal with. Now, I had a couple other videos, which are also not going to work, I'm assuming. So let me just pull those up. Host migration. Yeah, here we are. Okay, so this first example, I'm going to launch 2 servers and a client. The servers are those small windows sort of on the right-hand side there. And you can actually see visually which entities are in the authoritative role. Those have sort of got a black outline around them. The light blue outlines means they're in either in a client role or in a proxy role. So I'm going to boot up another server here, just to demonstrate some of these operations in action. So here comes the second server. You can see they communicate together. They've cut the load of the world in half so that the simulation is distributed. My client is still connected. My client didn't disconnect during this process, and it's actually still interactive. So if you're actually running around on the client doing stuff, you would not have even noticed this. This is a seamless operation from the client's perspective. I'm going to shut down the first server now. This is the server that we initially connected to. And just show you that the client is still responsive, and the remaining server has actually picked up authority over everything in the game world. And there's no loss there. Like actually, if you're running around there, that client migration is seamless. There's no corrections involved. And just to show you that this is not always like a controlled operation. So I'm going to launch 2 servers, and I'm going to crash one of the servers, essentially. I'm going to just kill it. And really what this is to demonstrate is that migration may not happen under controlled circumstances. We may not know. Like there may not be any warning. There's a number of reasons for this, right? Like your server could lose power, cables could get disconnected, like your application itself could just crash, hardware failures. Like it's really hard to predict when stuff is going to crash. And as we start scaling up the number of servers, so like I showed you 4 servers there, but there's nothing stopping you from going to like 40,000 servers or 4 million servers. The probability that any one server is going to fail is pretty high when you start dealing with numbers like that. And that means like when you start really scaling this stuff up, we need some mechanism for fault tolerance across the entirety of the simulation. We can't like disconnect 1 million players if just one of our servers goes down. That means we need like elegant mechanisms for host migration, even in uncontrolled circumstances, and that's what that shows. Okay, so I'm going to jump into the communication mechanisms now. The first is the network properties. Network properties are something you're familiar with if you saw Gene's talk. They've got a number of very interesting attributes. Primarily, they've got the type and the name, which are what you're going to interact with the most. But for our perspective, with this talk, the 2 that I'm most interested in are the replicate from and the replicate to fields. Now these fields, they take a subset of the network entity roles that we talked about in the beginning of the talk. Replicate from, you can just sort of walk this through, is like who's replicating the data to where. So you can imagine it only makes sense for things that have write access to be able to replicate, because if you've got read-only access, like you're not changing any data, there's no reason to replicate. So replicate from takes exactly these 2 network roles. Replicate from. Replicate to can take any of the roles. But the cross product of valid roles here is quite limited. Like this is the full set of all the valid from and to roles inside the engine. As you can imagine, most of them are the authoritative role. So it's from the server replicating to other roles within the simulation. And in fact, there's like a kind of a hierarchy of replication here going on. So like if I say something replicates from authority to client, it's also going to replicate to the roles underneath of that. It's also going to replicate to authority, to autonomous, and it's also going to replicate to server. It's just an implied thing. If I say replicate from authority to autonomous, it's also going to replicate to the server role. The last one here, autonomous to authority, this is pretty special. It's a way for us to basically write, we use it mainly for client metrics, right? So like if you want the server to know about the frame rate, the memory usage, VRAM usage, like metrics about your client's status, so that your server can basically monitor the health of your game as you deploy new content and new patches. This replicate from autonomous to authority allows you to basically use the same delta replication mechanisms that the rest of our game state uses to replicate that state back up to the server. That said, you can use it for very nefarious purposes. There's nothing stopping you from going into the transform component and making that replicate from autonomous to authority. And then you're effectively client authoritative at that point. If you do that, it's evil. You're going to get hacked, but it's possible to do, so I recommend you don't. So entities can migrate. The rules around that migration are quite arbitrary. They're not even implemented inside the engine itself. They're up to the implementer of the large world functionality. And because those rules are arbitrary, our network needs persistent and consistent awareness of all the state of the network relevant simulation at all times, right? What that comes down to is the fact that just raw member variables on things are actually quite dangerous. If you store state in a member variable and that entity migrates, the network has no idea it exists, so it's going to be lost. So just as an example, you wouldn't actually write something like this, but I make my own component that inherits from a multiplayer component, and I add some local variable there, my Boolean doing something interesting. It's set to false. I'm playing around on my computer. I do something. That flag gets raised to true, and now my client is doing something very interesting. And now the server that I'm connected to crashes, and my game state migrates. The network had no idea that you set that flag to true. It's not in a network property. And so it's going to get reset to false as soon as you migrate, and obviously you're not going to behave properly. So we've got the solution for that, and that's these authoritative to server network properties. If you put any state into a network property that's marked like this, it's only going to replicate to other servers that can see your entity. So other servers that have awareness of your entity. And what that basically means is that if you store all of your authoritative state inside these properties, that server that can actually see your entity is capable of assuming authority over your entity at just a moment's notice, just almost immediately. So the Boolean member variable example, this is what you'd want to do instead, right? You'd want to actually create a network property, bool, something interesting, set your rules for replicate from authority, set it to the server, and everything will be good. This means if your entity migrates, whether it's expected or unexpected, your state is going to be preserved and it'll continue functioning correctly. I'm going to jump over to the remote procedure calls. This is the other communication mechanism we provide in the engine. These are basically fire and forget method calls, right? So it's a function call, but there's no return value. There are two interesting properties for these remote procedure calls as well, the invoke from and the handle on. And as before, they take a subset of the network entity roles we talked about in the beginning of the talk. And the roles here, they're really there primarily for security purposes. You can imagine I make a game and I put an RPC on one of my entities that's deal damage. If you allowed clients to send a message up to the server saying deal damage to any arbitrary entity, you're going to get hacked pretty fast because they're going to deal damage to everything they don't like. So you'd want to restrict that RPC to only being able to be invoked from the server role. And that basically means if you had two servers and they're communicating and one entity decides to do damage to the other, you'd trust that server and say, okay, you can send me this RPC and I'll process it as you expect. The handle on tells the network which network roles should be handling this remote procedure call, right? So if you say handle on authority, that network message, that RPC will get forwarded to the server that has authority for that entity, and that's who's going to actually process that message for you. If you say handle on autonomous, it's going to go to just the player on the local client. Remember the client screen, they had the orange player. It's going to go only to that client, only to that entity, and that's who's going to process it. So for example, our corrections that we do for local prediction, those are server to autonomous remote procedure calls. Client actually goes out to everything that can see that entity, everything that's got a client. which is crazy. It'll send it out to tons of objects. But this is actually really useful for things like effects. So like particle effects, explosions, like just things that are not necessarily simulation relevant, but just make it look nice. Okay, so going back to the controllers again, controllers represent write access to our components. And there's two forms a controller can be in, either an autonomous on the client, so the predictive controller, or authoritative, the server. And these controllers, we don't really hide them by default, but they're intended to be hidden by default, and they're intended to be hidden for a very good reason. That's because we don't actually make assumptions that there's going to be a single server inside Open3D Engine. So I'm just going to give you some bad code here first. Here's just a network entity handle, and I'm going to try and directly access the controller. So I'm going to access the multiplayer weapons component here, and if the controller exists, I'm going to do stuff, right? And now you can imagine, like, I'm just developing this feature locally, and I'm testing on my machine. When I'm testing on my machine, I'm probably only using a single server. So this controller, because it's running on a single server, it's always going to exist on the server that I'm testing on. There's only a single server. So that condition will always branch true. Like, that logic will always get executed. The problem is, when you actually deploy this, and if this does scale up, and you suddenly have, n servers, that logic's no longer going to execute like you had in your local machine, because your controller probably doesn't exist, right? The authority probably exists on a completely different host from the server you're running this logic on. So don't do this. Instead, you'd want to write a remote procedure call. So in this case, if it's a server privileged operation, we do invoke from server. That means anyone that has that entity in a server role, so that means like any of the servers in your simulation, they can invoke this RPC and handle on the authority. Now, as soon as you do this, the network layer, it understands this, right? It says like, hey, you've told me to send this message and process it on the authority. The server actually knows where all the entities are across like all the hosts, and it understands which ones are in the client role, which are in the autonomous role, and which are in the server roles. So it can do this. It can actually forward that message to the correct server on your behalf. So now if you rewrite that same logic and access the components are always guaranteed to exist. If you can see that entity, all of the components that are there will exist, right? That means the conditional for the component is always going to branch true. And instead of the direct method access, I'm going to call do stuff. It looks like a method access, but it's actually an RPC invocation. So this is the point where the network sort of steps in and says, okay, I got this message now. I know who to forward it to. I'm going to do that for you. And now, even though your entities are migrating around in real time, the network layer will actually handle that for you. It'll actually forward these messages to the correct host, and all of your logic will continue working, even if you have 1,000 servers instead of one. So this is the right approach for messaging to the things that have write access. So I'm going to go into the interfaces now. There's a couple interfaces that are important. The first is the replication window. You can think of this as like a window into the screen of another server. Really the important thing here is the is-in-window method, the pure virtual there. You'd implement this in order to say like, hey, like this is what I'm interested in. This is my area. In fact, we use the same interface for server-to-client replication. The other interface of interest are entity domains. And this really defines what entities the server controls. So you can imagine, like, you can come up with any sort of concepts for this. Like, I want a server to control all the players in my simulation, or I want a server to control all the AI, or I want my servers to round robin entities between them all. So you could do something modulo the net entity ID, and that would be like who you actually control. Or you can do, in my videos, like a spatial thing where you cut the world up and servers are responsible for a geographical, like, subregion. That's all up to your control. The handle loss of method there, that is for the fault tolerance piece. So when you lose the authoritative replicator, that's what's going to get invoked, and that's how you can actually recover control of that entity. Okay, so I'm going to do a quick recap because I'm running out of time. So large worlds imply scalable server solutions. As soon as you have scalable server solutions, you kind of need host migration for a number of reasons, fault tolerance, and just for elastic scalability, so you can react to things running around and clustering together. If you've got host migration, it's really important that our server be aware of all network state all the time. And that's why the authority to server network properties is so important for large-scale simulations. As well, like if you're talking about large-scale friendly server simulations, you don't want to have direct access to the controllers because you don't know who has authority for your entity. That could be any server anywhere. So it's really important that you do all your messaging with RPCs and never directly access the controller. So at this point, I'd like to cut the camera and we'll do the questions. I tried Stable Diffusion for this too, and it also did not work very well.
Unfortunately, we are at times. You won't have time for questions, but is there any place that people can reach out to you if they have additional?
Sure, I'll just lobby.
Perfect, thank you.
Yeah, my email or my Twitter are there too. Okay, thanks, Al.